Okay, so I've already done a video on this thing, differential calculus. So you should watch that video first, and then you'll understand some of the basic things that they are introducing over here. So first of all, we have ordinary derivative, which you know of. Then you got partial derivative and stuff. Then you have the gradient, which I talked about in that video and also a video before that, right? So I won't be explaining any of this thing. You can watch that video if you really want. Okay. Then the next thing is, okay, so you got a problem now. Find the gradient of r is equal to square root of x square plus y square plus z square, the magnitude of the position vector. Fine, yeah. So what we can do is, like square this thing. So r squared is equal to x square plus y square plus z square. Then differentiate this, but then we'll just keep y and z constant. So that basically you're taking a partial derivative, right? So what you get is like 2r partial r upon partial x is equal to 2x. So partial r upon partial x, that is just, x upon r. And similarly, partial r upon partial y will be x upon r and so on. Y upon r, of course, and so on. So basically what you get is this thing x, y, z, and that thing upon r. And yeah, I mean, this thing is just r vector. So like this happens to be r hat. So r hat is the gradient of this thing, which is, yeah, exactly what they got. Instead, they just did the whole thing. Yes, same stuff. You got x upon r. This whole thing is just r, right? Yeah. Okay. Then problem 1.11, find the gradient of the following functions. So you got x squared plus y cube plus z power 4, whatever. This is just too basic, not even worth my time. But like whatever, I'm gonna do it orally. So you got 2x, then 3y square and 4z cube. That's the first guy's gradient. Then what about this guy? You got 2xy cube z power 4. Then the y coordinate you have 3x square y square z power 4. Then next you have 4x square y cube z power 3, right? Okay, what about this one? You know the thing, just differentiate with respect to x, put in the x coordinate with respect to y coordinate, get the thing, right? You don't actually have to do this. Okay, then you got problem 1.12. The height of a certain hill in feet is given by this thing, where y is the distance, north, x is the distance, east of south, Hadley, I don't know, some place. So, right, some place, x is distance, east of that, this thing is north of that. Got it, got it. Okay, xy system, whatever. The height of a certain hill is given by this thing, so it's all z coordinate, whatever. Where is the top of the hill located? So first of all, um, we already know that the gradient basically it gives us the direction in which you have to move in the xy plane so that your h value increases, or yeah, basically that. So when the gradient will be 0, that is basically saying that you cannot move anywhere now, just that your h value will increase. So that just means you are at the local maxima, right? Or it will also be local minima, such that in any place you move, you will get an increase anyway. So it cannot decide a direction yet. So yeah, at local maxima or local minima, you will have the gradient being 0, right? Okay, but how do we ensure that it's the local maxima? Well, if you just think about it like this, you got x and y, right, like this. This is x, this thing is y, this thing is our z or h coordinate. You have some 3D thing like surface over here. We'll just take a slice of this thing with y is equal to some constant, right? Then as you move up, your x derivatives, like basically partial f upon partial h upon partial x, that's this slope, right? So this thing is changing at this point, it just becomes equal to 0. If this is a maxima, then from usual calculus, you know that this should have the second derivative being negative, because the slope is decreasing, right? So yeah, the condition that we have is that partial h upon partial x is equal to 0, and partial h square upon partial x square, that should be less than 0. And similar stuff for y as well, right? So let's see. First, we'll just do these two equations: differentiate with respect to x and equate to 0, and also y and equate to 0. Let's see what we get. So what do you get? Just get 2y minus 6x. Well, that's constant now with respect to y. Okay, then you got minus 18. This should be equal to 0, so like y minus 3x minus 9. That's equal to 0. I think, yeah. Well, that's gone. This thing is just minus 6x. This thing would be 2y. Yeah, I guess so. So Just got y minus 3x minus 9 equal to 0. Right, that's our first equation. And also like this thing is the first derivative with respect to x, right? So the second derivative, that would just be negative 6, which is negative already, which means that yeah, in terms of x, this is like maxima wherever this equation is being followed. What about the y1? If you differentiate to y, what you get is like 2x, then that's constant to y, it just doesn't matter. Then you got this thing minus 8y, so plus 28, and that's equal to 0, right? Which is like, okay, this is the first derivative. What about the second derivative? The second derivative would just be negative 8. So that is also negative. So yeah, it is in fact the local maximum, right? And you know, this just becomes x minus 4y plus uh, 14 is equal to 0, I guess. Yeah, so that's like x plus 14 is equal to 4 times of y, but y is just 3x plus 9. So yeah, like 4 times of that is 12x plus 36, I guess. Yeah, 3x plus 9, right? Mm. I'm still double checking. So like minus 6x over there. Then you got, this is not there. This one is just negative 18, sure. Divided by 2, just get y minus 3x minus 9. Yep, looks correct. Then you got like 4y, just 2 times of that is 12x plus 36. Makes sense. Yes. So what you get is like 11x is equal to negative uh, negative 22. Okay, so x is equal to negative 2. That's the thing. So that just means y is equal to 3x plus 9 is equal to negative 6 plus 9, which is 3. So x equal to negative 2, y equal to 3. That's where you have the maximum value, right? And yeah, this is like, you know, something like the left hand side of a conic section or something like that. So yeah, this thing, this is a nice thing. That is that this really is our maximum value, and then as it goes to like infinity or stuff, you know, like x goes to infinity, this just becomes very negative because you got x square over here. Y is finite value, x goes to infinity, this would just become negative infinity. So that's definitely not going to work, right? So at the infinity values, yeah, you're not getting the maximum value, right? This is the maximum that we just got. Okay, cool, whatever. So where's the top of the hill located? It's negative 2 comma 3. How high is the hill? Just put that in this function. Let's see what our edge will turn out to be. Oh, and also, do you want anything else? How steep is this? And also, actually, everywhere that we did the derivative, it should contain this 10 as well. So this should be like 10 times of that. This should also be 10 times of that. But whatever. Right. Where is the top of the hill located? We already got that. How high is the hill? Just put this into that. We can do it. No big deal. How steep is the slope? Okay, at a point 1 mile north, and so like x equal to 1 mile east. Okay, it's like no. Oh, okay, x equal to 1 because like okay, 1 mile east, that's just x equal to 1, and 1 mile north, that means y equal to 1. Whatever. Sorry. It's just that they have a weird way of saying this. Anyway, so 1 comma 1, that's the point that we're talking about. Fine. So at that point, whatever gradient we have, just take the magnitude of that gradient, and there you go. That's your slope. Um, Not that bad, I guess. I mean, we already know this is the radius form. Okay, just 20 times of this guy, right? Yeah, 20 times of this. So this is the x coordinate, this is the y coordinate. Just put 1 in there, 1 in there. Just get like 1 minus 3 minus 9, which is minus 11. So you got minus 11, and what this one? Minus 4, that's 10, 10, 11. Okay. So what you get is just 20 times 11 times square root 2, which is 220 square root 2. So that's the slope, basically. Feet per mile. I'm not going to do that. Definitely not going to do that. Wait, what is edge, by the way? Y is distance in miles. So this is per mile. Ah, fine. And x is distance in... Okay. Oh, this is in feet. Fine. Then the unit system makes sense. So, yeah. That would be the thing, of course. 220 square root of 2. Those many feet per mile. Yep. That should do it. Okay. That's awesome. So you got the answers of these guys. How high is the hill? This didn't actually give that answer. Who cares? Just put these numbers in, get the thing. Okay, next question. Let small r be the cursive r, be the separation vector from a fixed point x dash y dash z dash to a point x y z, and this be its length. Show that the gradient of r squared is equal to 2r. Okay, the gradient of 1 upon r equal to negative r hat upon r squared. What is the general formula? You know what, I'm gonna do c right now, and then we'll do a and b, because this is n equal to, this is n equal to negative 1 or something like that. I mean, okay, this might be complicated, but whatever, we'll just try it out. So what's the gradient of r power n, right? Okay, uh yeah, okay, to the point this time. You know what I'm thinking? Let's say x dash y dash z dash is equal to 0 0 0, because it doesn't matter anyway, right? Yeah, because like partial of 1 partial x is the same thing as saying partial of 1 partial x minus x naught, x minus x dash, right? Yeah, because this thing is a fixed thing and this point is varying, I suppose. Yeah, that's gotta be the thing. Here when you say the gradient, right, it's a fixed point. They actually told us in the question itself it's a fixed point. So you know what, just make that to be equal to 0, right? Make that equal to the origin, and right, and you just have cursive r everywhere. You don't have the actual position vector with respect to the actual origin. So might as well just make this the origin, right? So of course just make this 0 0 0. Now we can do this thing. So you want the gradient of r power n, which is like, okay, you got partial x of r power n, that would just be n r power n minus 1, then partial r upon partial x, which we just saw is going to be x upon r. This is like n r power n minus 2, and then you got x, right? And then this is going to be for y and z and so on. So basically what you get is like n r power n minus 2 r vector, or this vector, whatever. So basically n r power n minus 1 r hat. That should do it. Yeah. So for example, when you put n equal to 2, this would just be n times r hat. It's like n r hat, of course. In this case, n is just 2, so 2 r hat makes sense. When you put negative 1, right, n equal to negative 1, we just get n r power negative 2, and then you got this. Yeah, I guess that makes sense. Is there like division by 0 anywhere? No, it's not. So you sure can do this. Easy as that. So it's negative 1, right? N should be negative 1. So negative 1, then you got r power negative 2, and then r hat. Which, yeah, that's exactly what I'm talking about. This is the thing. Okay, next. Okay, then wait, you have another one? So that f is a function of, oh, suppose that f is a function of two variables. Show that the gradient is, okay, what? It transforms as a vector under rotations. So they give a hint as well. The hint is that partial f upon partial y bar is equal to partial f upon partial y upon partial y bar plus partial f upon partial z. Okay. And the analogous formula for partial f upon partial z bar. What is y bar and z bar though? And what is this f evaluated at? Is this at y and z, or is it at y bar and z bar? You know that y bar is equal to this thing. So basically, yeah, okay, it's given as a function of y and z, whatever. And z bar is also given as a function of y and z. Fine, what about it? Solve these equations for y and z as functions of y bar and z bar. Fine. Look, I completely understand what these equations are. This is just a multivariable chain rule. This too is, just multivariable chain rule for partial f upon partial z bar. But I don't get the geometrical interpretation. What are y bar and z bar? Oh, actually they did tell us. Okay, fine. Y bar and z bar are just the, okay, it's like y z. You got a point, then you apply linear transformation on this thing. Basically, let's rotate by phi. It's just like whatever, anti-clockwise, clockwise. You're doing a transformation. Now it's some point over there. Okay, awesome. And this thing, this is like multivariable chain rule. It's used usually when you have f of evaluated at y and z. So whenever they said f, they are actually meaning f of y and z, right? Yeah, they don't mean f of y bar and z bar, because that would of course mean you are evaluated at the point where it, yeah, okay, that would not be correct. Definitely not be correct. So it's just f of y and z. Sure. So what they're saying is like when you change y bar and z bar, how does your f change? Well, that's weird. Wait, how is this related to gradient once again? This is just a multivariable chain rule. There's nothing like you solve these two equations for y and z as functions of y bar and z bar. Fine. So you got y and z as functions of y bar and z bar. Then you will put that into this thing. You will get partial f upon partial y bar is a function of y bar completely, right? Yeah. I mean, okay, f of y and z. You can just put y as a function of y bar and z bar in that thing, and basically what you get, what you will get is like g of y bar and z bar. Makes sense. But what after that? Uh, okay. This is very weird. Function of is what do we actually have to prove? I don't get it. What is it that we're trying to prove? What do they mean when they say that f is a like? Okay, what do they mean when they say that this gradient transforms as a vector under rotations? Wait, how does a vector transform under rotation again? It just rotates, of course, about the origin. So, huh? Wait a second. No, this is not making sense. Let's think about it still. So, what do you have? Something like this. You have a point yz. At this point, you have a function f, and then there's the usual gradient, which is pointing somewhere. So, yeah. Then you got y bar, z bar, which is either like this vector rotated clockwise or anti-clockwise. I don't know. We'll figure that out. So, if it's like this, okay, cool. Um, right. Y z r is like y z r is rotated forms of these vectors or something like that. Sure. And when we say like partial f upon partial y bar, what does that mean? I still don't understand this. What's actually going on? Okay, think about it. What exactly is y bar though? It's the yeah, it's the y coordinate of this thing when it undergoes a transformation. Sure, that looks okay, but this is weird. Let's think about it. Let's think about our dr vector thing. So, if you move from this point by a vector dr vector, right? Then over here, the vector with which you are supposed to be moving, right? So when you apply the inverse transformation and you get this thing or whatever, yeah, it's just a rotated vector, of course. And this is actually equal to our dy bar comma dz bar, right? Yeah, well, that makes sense, sure. But what about it? Then this is very weird. Sure, the radius vector changes like that, but what about it? What do you want to prove though? And okay, the gradient. It's the same function, right? The function is still divided by y and z. It's just that the gradient is now, oh, it's like partial upon partial y bar, comma partial upon partial z bar, right? Yeah, okay, that's what it is. Oh, okay. So what we actually have to do is not rotate the point. We have to rotate ourselves. Right. Right. So under rotations, exactly what's happening is that the point still remains there because the function, well, that's evaluated at this point, sure. Even when you changed it, the value of the function is not changing, right? Still at y and z. So couldn't it be like, you could interpret it like this thing that this point remains the same, just the way we are perceiving this point, like the way we are measuring where this point is, what are its coordinates. So that thing is changed because we changed our point of view, right? So all we are doing is just rotating this thing. Oh yeah, okay, that makes sense. Sure. Right, okay, so what is basically saying is that doesn't matter what kind of coordinate frame you have, your gradient is still the same. I mean, rotated coordinate frame, then your gradient is still the same. Yeah, that looks right. Of course, that looks kind of right. I mean, okay, of course, our Wait, if we apply linear transformation to the whole thing, then this is not going good, isn't it? No, this is not going good. It's I know it's more general than that. It's not just rotation. Like there's translation as well, and then there's some other kind of thing going on. Rotation about some axis that is not the XYZ axis. It could be a lot of different things, right? And all that we're actually doing is that like we are geometrically not changing anything. We're just changing our point of view so that the numbers change, right? Yeah, and the vector is still the same. Makes sense. That sure makes sense. And of course, we should have y bar hat in z bar hat, right? For our gradient. Yeah, yeah, that makes sense. Mm-hmm. Still weird though. Sure, so you got like these two values, right? But what about them? I mean, fine, you're gonna get that in you will get those values, but what next? You have to figure out what y bar hat and z bar hat is, right? Because now your coordinate frame is changed. So this does not actually convey the whole story. I mean, the question didn't, yeah, it left that as something we have to figure out ourselves. Honestly, this is just just a special case. It should be more general than this, right? We should be doing this for a all kinds of transformation which you know which have the transform basis vectors still being orthogonal and the same length and the same orientation, of course. Yeah, should have something like that. Okay, this is getting weird. Uh, Other than linear transformations, can we do some other transformation? No, I don't think so. You don't want to be squishing the vector. No, you don't want to be doing that because then the rate of change, yeah, that would change. So it has to be a linear transformation, plus it has to be a transformation that is orthogonal with the same orientation, determinant one and stuff like that. Okay. And then the unit vectors that we're talking about, right? So in this case, the new gradient that we are seeing, that's not just partial f upon partial y bar y hat plus partial f upon partial z bar z hat. No, it's partial it's partial f upon partial y bar hat. It's a different thing, right? Yeah, it's definitely a different thing. Well, whatever. For now, we won't do this because it's just unnecessary and not general. Anyway, so to the next one, operator del. The gradient has the formal appearance of a vector del multiplying a scalar. Yeah, we all know about that. Just see that video that I uploaded and you understand what they're talking about. Right, whatever. So divergence. You got examples? Cool. Wait, we are not supposed to be doing this? Okay, just give me problems then. Calculate the divergence of the following vector functions. Fine. So we got x square comma 3 phi z square minus 2xy and z whatever. First, take the partial derivatives to x of the x coordinate thing, which is just 2x, and you know we want divergence, right? Okay, just you got 2x, and then add to that uh, the partial derivative to y of the y coordinate stuff, which is just 2z. Wait, okay, that's for the second problem. We want the first problem. Sorry, that would just be 0 in this case. So you got 2x plus 0, and then last one will just be negative 2x. So that's 0 once again. So the first has 0 divergence. Or the second one, uh, y, then plus 2z, then plus 3x. I don't know. Plus 3x. All right. Yeah, that's right. Sure. Okay. The next one, 0. Then this will be this y, of course, which is 2x over there, and then you got this to z, which is just 2y. So yeah, these are the answers. Next. 1.16, sketch this vector function and compute its divergence. The answer may surprise you. Well, I want to be surprised. Let's see what's going on. So, oh, this looks a lot like, okay, so it's like electrostatic field. It looks like that. Maybe that's why they're trying to make us do this. Sure. So you want to figure out its divergence. Okay. It's 1 upon r squared times r hat, which if you think on it, you can write like this thing as r vector upon r cube, right? Yes, what do you want? You want partial upon partial x of this. Oh, first of all, you should actually write like this thing. X, Y, Z. So the x component is just x upon r cube, differentiate that to x only, right? So what would that be? It's like just 1 upon r cube. Then this is r power negative 3. So you got like negative 3, r power negative 4. That's that x, and then you got dr upon dx, which we know is just x upon r, right? It's partial r upon partial x, not dr upon dx, which is just x upon r. So just pick down something like x squared upon r once again. Yeah, you got r power 5 over there. So, 1 upon r cube minus 3x squared upon r power 5. That's what this thing will be. Then with respect to y, and then with respect to z, you want to differentiate this guy, then this guy. You get the thing. So just sum this up, cyclic summation, of course, because symmetry. So you just get 3 upon r cubed minus 3 times of x plus y squared plus z squared. That's just r squared. So r squared upon r power 5. That's this. Okay, that's 0. Oh, so what I'm basically saying is that, yeah, I mean, this has 0 divergence. Okay. Nice, I guess. Right, the answer may surprise you. Can you explain it? There's nothing like explaining it. It is 0 divergence. That's what the math says. Oh, wait. Like physically divergence is just flux upon volume. So it's actually right. You should actually first of all sketch this vector function because that might be an important part of it. So you got the origin from which you have the field going. This is the highest field. I'm saying, I mean, it is like a vector field, but you can also think of it like electrostatic field or something like that, right? So you got this field going, then this decreases its magnitude, right? Whatever, that's how the function will be. So you got some random point over here, then at that point there's no divergence. Basically, when you have like a volume around it, then there's, yeah, the total flux through this surface is 0. That's what we're saying. Sure. Kind of weird though. Is that the case? Flux through that is actually 0. Huh? Yeah, I mean, we could relate it to a lot of stuff, but I don't want to be relating it just now because they will probably get into those details, right? So let's not actually do that. And wait a second. All right. Yeah, what's I gonna do? So yeah, no problem with that. At this point, it is 0 divergence. What about it? There's nothing suspicious over there. Computed divergence. I did. It's 0. But wait. Divergence. Oh, okay. At this point, of course. Okay, at this point, there is divergence, right? Yeah. Okay, that must be what they're talking about. This may surprise you. Not exactly. I mean, I read this book once. When I say once, I mean like very partially, just looked over it, and then I saw all the nice things you are going to mention. So I think I get where it's going. That here it's supposed to be diverging out, but then it's 0. That can't be the case. But the thing is, divergence, it only works like in general. This stuff only works like gradient and curl and divergence. This only works when the field is continuous, right? Look at this guy though. At this part, the field is going to this direction, and now it's going in the completely opposite direction, and it's not 0. It's actually there. It has some magnitude, so it changed its direction completely. The field is discontinuous at this point, right? So no, there's no suspicious activity going on. The thing is, it's discontinuous at that point, so you can't think about partial differentiation at all. So how are you going to define a divergence? You could do the flux upon volume thing. That would just mean like the divergence over here is like infinite or something because, yeah. What do you have? Just got this field 1 upon r squared times r hat. Let's just take take a sphere with radius r, small r of course, around this thing, and let's see what happens as r tends to 0. What happens to our uh, limit, like the limit we use to calculate divergence. If you know, you know, right? You should watch that video of mine where I explain what divergence is in more abstract form, right? So this is our field that times the area is just 4 pi r squared upon the volume 4 third pi r cubed. What do you get? You just get 3 upon r cubed as the, what do we call it? As the thing that we have to limit. So r tends to 0 plus, of course, 0 plus r is a positive number. This thing tends to infinity. So divergence does go to infinity in that case. Which means, yeah, like at this point, divergence is infinite, and at any other point, it's 0. Huh. This may surprise you. Well, not exactly, because, there's this discontinuity, so there's nothing surprising at all. If this is the function we're dealing with, it's actually very bad kind of function, so of course it would happen like that. On the other hand, if you took something like r vector, just r vector, then yeah, like there would be no discontinuity, because at 0 comma 0 comma 0 the r vector thing is 0. So anyway, next, into dimensions show that the divergence transforms as a scalar under rotation. Okay. All right. Once again, the same stuff. Once again, we are changing our coordinates. Like we're changing our axis, basically rotating our reference frame, right? Without changing the actual graph, we're just rotating our reference frame so that our numbers for our coordinates would be different. It still is the same thing though. Still referring to the same stuff, right? So our aim is to show that what? Partial Vy upon partial y plus partial. Okay, whatever. Wait. Are you serious? Wait a second. That doesn't look correct though. V bar. Right, okay. In the new reference frame, it's supposed to be like that, right? After the transformation, the y coordinate that you get is actually not the y coordinate. It's the y bar coordinate. So when we say v bar y, what we are referring to is actually the component in the y bar direction, not in the y direction. So yeah, this would make sense. This would actually make sense. So that's what we want to prove, that divergence thing is like, you know what? I'm not going to prove that. I'm going to leave this as an exercise. I already gave you the most general proof you could have by basically defining divergence in a more abstract form, right? Like flux upon volume. So it's still the same. Yeah, it's still the same because the actual graph didn't change. Our vectors are still in the same. How do I even like describe it? It's still the same shape. That's what I have to say. Yeah, that's what I will have to say. Just our reference frame changed. So the flux does not change, your volume did not change. So yeah, the divergence is still the same, of course. No surprise at all, right? And when you will do this, and I don't think I will do this. So if you do this, you will see that it is the same. Otherwise, why would they put this as a problem? Anyway, next. Once in the same strategy, you have to express, uh, what do we call it? You have to express this thing in terms of y and z completely. So you can write like partial, I think you can do this thing, partial v bar y upon partial y bar. Well, that can be written as partial v bar y upon partial y and then partial y upon partial y. Or you can go for the right hand side, but whatever. Now you can write everything in terms of y bar and z bar by solving the equation for, like to get y and z, just like the way they did, right? Or you could do the other way actually. Whatever. So you got this thing, and yeah, I guess this should actually work out. Right. Oh, and of course, this thing is actually already a function of y and z. Like our vy bar, that will be already given as a function of y and z. Because I mean, we are assuming your v was initially a function of y and z, and then you just apply some kind of transformation on this guy, and now it's still a function of y and z, just a different function, right? So yeah, this part is doable. Then this part you can also do. You can figure out what y bar is. Actually, you already know what y bar is, a function of y and z. So then you can do like this is just dividing by this thing, partial y bar upon partial y. Yeah, it's like the same stuff. Once again, the same principle. Keep everything else constant, right? Oh shit! No, no, no. It's not the same. It's not the same. You can't do it like the usual derivative. Okay, right. I almost forgot that. Fine. So this is actually different because you have to keep y bar the same. You don't have to keep y same. You have to keep y bar same. Does that make sense? So you have to in fact write y as a function of y bar z bar, and then you have to differentiate. Okay, whatever. This is only one part though. You got this thing as well. Partial vy bar upon partial z, and then you got partial z upon partial y bar, right? So yeah, awesome. Do this thing, and okay, I guess. Similarly do this thing, add them, and then this you can already calculate, so no big deal with that. Uh, Wait, 1.29, and what is our vector field that we're actually dealing with? 0.29. Whatever. I mean, I'm gonna leave that as an exercise for you people, right? Okay, next, the curl. In the definition of del, we construct the curl. Okay, notice the curl of vector. Yeah, whatever. You already know this. So, like this intuition that it's actually like how much it's swirling around this thing, that is kind of not the way to define it, right? No, curl shouldn't be a measure of how much it's, yeah, how much it's like curling. Yeah, that's what you have to say about a certain point. No, because that's like saying that temperature is the degree of hotness and coldness. We still don't know what exactly curl is. Like, what does it measure? For example, if curl was some kind of representation of angular velocity, which it is, by the way, then it would have made more sense. And okay, so let me just tell you the thing straightforwardly. In the case when your vector field is given by this thing, r vector cross omega vector, where omega vector is a fixed vector and r vector is the usual stuff x, y, z. If this happens, yeah, like your vector field is given by this thing, in that case, this curl thing is just 2 times omega. Yeah, it's just 2 times omega. That's what the curl is. And right, the units match up. You got v vector, whatever unit v vector has upon length. And over here as well, getting partial 1, partial x. So partial x is having length. Partial itself, just an operation, it doesn't have a length. So, like partial v upon partial x, that is v vector's unit upon length. So the same thing as omega vector, right? So the units match up, and it turns out like this thing is actually just 2 omega vector, right? Just put this in there and actually calculate the whole thing. You will see it's the same thing as this. And yeah, this is only for the special case when your v vector is given by something like that. Otherwise, it's hard to do that. Right. You could just do this thing like it's equal to this guy plus something along the r hat direction. So f of, it's like f, just f is a function of x, y, z, and that's in the r hat direction, something like that. And then you try to figure out what the curl should be at the origin or something like that, right? Yeah. Then how would it actually be though? I mean, again, when you think about it in the abstract term, this thing should not matter at all because you know it doesn't, yeah, factor in the integral I'm talking about, like this loop integral, right? The loop integral of v vector dot dl vector, right? And yeah, we have to actually divide this by the area, the limit as a tends to 0 of this thing, you know the thing, right? So it's a dot product over there, and then dl vector is actually perpendicular to our r hat, since we're talking about a circle, something like that. If we talk about a circle, that is. Then yeah, like this would mean, you know, what was I going to say? Right, that this actually does not matter in the end. So, I don't know. I wouldn't say it's exactly angular velocity or something like that, because it's not a rigid body we're talking about, right? It's not that all these points have a single angular velocity and like a single center of rotation. No, that's not the thing. It's much more complicated than that. I mean, if it was somehow related to angular momentum, that would be really nice, because angular momentum does not require a rigid body. It can be for any kind of system. Uh, but then again, how does that represent swirling? Maybe it does, because we use it for rotational dynamics. Still, it's weird. Anyway, for now, just think of curl as this thing, this limit, without going into the physical meaning too much, right? Anyway, next. Okay, got an example we don't care about. Problem 1.18. Calculate the curl of the vector fields. Oh, come on. Seriously. 1.15. What? I'm not scrolling up just to see that. Consider a vector function that has zero divergence and zero curl everywhere. The constant will do the job, of course, but make it something a little more interesting than that. Okay, a vector function that has zero divergence and zero curl. Wow. Okay. And there could be multiple such functions. Actually, a lot of such functions, in fact. Uh, I don't know. You could have so many such, like any function that has only a radial unit. Well, yeah, that has zero curl, so that could work. Or okay, we'll think about it. But no, the thing is, the curl is only zero around the origin if it has a radial. Right, right. I mean, okay, there's one thing we know, that if the curl is zero, that would mean that whatever field we are talking about, that is conserved. Okay, this is too advanced for you guys, isn't it? But this is a nice thing though, that because we define it like that, if you think of the field being like a force field, so a field representing force vectors at different positions, then this loop integral is basically the energy that a particle gains when it goes around that loop, right? And if a field is conservative, then the energy gain would be zero, because like that's the way it works, potential energy and stuff. So what that would mean is our curl would be zero everywhere. So for any conservative field, in fact, we should have zero curl, right? So what kind of conservative fields do we know? Every single field has an inverse square law. Okay, and we also just saw that the inverse square law thing also has zero divergence. You know where it's heading, right? There's a very, you know yeah, very nice example of a thing that has zero curl and zero divergence, which is just this, of course, right? Our 1 upon r square r hat thing, that works. It definitely works. Yeah. And of course a constant will also do a job. So a constant that could work, or 1 upon r square r hat thing, that could work. Some other thing, maybe, I don't know. um Hey, what's the divergence of this thing though? R power n. We already saw what the gradient is, but what about the divergence? We'll see. So just R power n, R hat. What's the divergence of this guy? Or you could just say this thing, R power n R vector, right? Okay. So the divergence of this guy. Right. You got x R power n differentiated to x, of course. Got R power n plus. What was I going to say? Wait, no, that was divergence that we actually calculated. Right. What was it? What was it? I think it was just n r power n minus 1, right? Yeah. Wait, was that divergence or what? Or was that a gradient? Why can't I remember it? No, it was a divergence. I'm sure of it. Oh, come on, I'm just gonna do it. Yeah, I'm just gonna do it, of course. So, r power n. No, that must not have been a divergence. If it was, it would be. Wait, I just have to see that now. Oh, and also, by the way, what problem they were talking about? Problem 1.15. We'll solve that as well. Ah, this is problem 1.15. So you want to figure out the curl of these guys. Okay. Uh, oh, come on. I just hate this. I don't want to be doing cross products and stuff. And moreover, these are very elemental functions, nothing of interest. Right? Just polynomial functions. Come on, you can do it yourself. I'm not gonna do that. Okay, where's that problem? We figured out divergence of the general thing. Del operator. Oh yeah, okay, fine. So you wanna show no, it's the gradient. It is the gradient, huh? Right. Okay, the general form for the gradient of r power n. Right. That was this thing. N r power n minus 1, and then you got something like r hat. That was a thing, I guess. Yes, just r hat over there. So that was gradient. That's not what we want. We want the divergence. Okay, let's try different. So you got x r power n. So the x you just get r power n, then you just get like n r power n minus 1 times x. I guess this is going correct. We got dr upon dx partial r partial x whatever. Just got x square upon r. So that's just r power n plus n r power n minus 2. Then you got x square. Very interesting. Wait, but shouldn't this also have been in there as well though? It should have been there. Something's going weird about this. Yeah, definitely it's going weird. Wait, something's not right about this. It's the partial x of r power n. Oh, that's a different. It's scalar, of course. So it's different. Yes, it's very different than that. Yeah, divergence is just the summation of this thing, cyclic summation, which would be how much is 3r power n. Should it be negative or something? No, it's not supposed to be negative, in fact. Then you got like what, plus n r power n minus 2, and then you got x plus y squared, which is just r squared, so that turns out to be n r power n. So basically you just get like n plus 3 times r power n. That's our divergence. So we want our divergence to be 0. There's only one way this could work. N is equal to negative 3, which would mean it's just r power 3. Oh, sorry, r power negative 3 r vector, which is, yeah, just r hat upon r power 2. So the only way something like this would give us zero divergence is if, you know, n was negative 3. So that's a dead end. I don't think we can figure out more functions with that kind of property. Yeah. I mean, of course, we can figure out some other like algebraic functions, something like that. But nice functions, I don't think we can figure out any nice functions that have this kind of property yet, at least. Okay. What were we doing once again? Yeah, this thing. Right, so we already got this r hat upon r squared thing that works perfectly. You got a constant, sure. I think that's enough, just move on. The calculation of ordinary derivative is facilitated by a number of general rules such as there is some rule, okay, whatever. Okay, so the gradient of f plus g is equal to gradient of f plus gradient of g. Yeah, easy. Partial differentiation is distributive, and this is just, you know, like x hat partial 1 partial x. That is distributive in the end. So we say this thing, of course. Then the divergence of sum of two vectors is sum of divergence. Yeah, sure. That also makes sense because like the dot product is also distributive, so you can do that. Yes. Yeah, it makes sense. Partial differentiation is distributive plus the dot product itself is distributive. So yeah, makes sense. Then what about this guy? Del crossed with a plus b. Once again, partial differentiation is distributive, so you can clearly split this. Yes. Like every operation you will do, everywhere instead of like, yeah, okay, everywhere, you know, okay, first of all, let's just say that a vector plus b vector equal to c vector. Then you'll do all kind of operations on c, and then any component of c, let's just say cx, that can be written as ax plus bx, and then in the end, the basic operation will be partial differentiation. So you can split that, right, and then you can collect terms, split out everything, because, you know, yeah, multiplication with a unit vector, that's also distributive for a scalar, right? So yeah, that explains it. Okay, and then you got this stuff. Come on, that's just trivial. You can do that. It's just, yeah, multiplication of constant over there. As you can check for yourself, product rules are not quite so simple. There are two ways to construct a scalar as the product of two functions. So you can have product of two scalar functions and the dot product of two vector functions and to make vector. Okay. Well, this one should be easy, right? It's just a multiple of that guy. That will be probably easy. Accordingly, there are six product rules, two for gradients. Okay, this is, yeah, this is understandable because partial on partial x of g, that would just be this thing like f partial upon partial x of g plus g partial upon partial x of f. So in the x component, you got that thing just split apart the the whole vector, and you get this thing. Yeah, that makes sense. Then you got this. What is this? I have no idea what this thing is. The gradient of a dot b. Huh. What? Okay, that's equal to a cross del cross b plus b cross del cross. Wow, that has escalated very quickly, don't you think? Okay, what is this exactly? What is e dot b? Let's just think about the x component first. So you only got like ax bx, right? So the partial x of that kind, that would just be what? That would be, right, like partial. You know what? Instead of writing ax everywhere, I'm gonna write just a vector. Oh, sorry, just a small a, right? So small a is the x input of capital A. That makes sense. So you got partial a upon partial x times b plus a partial b upon partial x. That's what we have in the x component. Let's see what's the x component of all of this. Okay, first you got the del cross b thing. So you got partial x, partial y. I guess at this point you should just actually put X subscript everywhere. Yeah, there's no other way. You just have to put these things. Okay, so what do you have? Just got px, py, bz, then this stuff. We just want the x component anyway, right? No, we don't. There's another cross product involved. Oh, come on. Seriously. Seriously. Is there some identity I can use for this kind of triple product? This is the usual product that I use, but that's not gonna work. No, that's not gonna work. You can't do it like the usual dot product stuff, so yeah, that definitely won't work. Okay, we'll just have to do it manually. So, since we only want the x component, uh, so what should we be thinking about? On the yz components of this guy? Yeah, the yz components of this guy. Seriously, what's the y component going to be? So you got this and that, which would just be partial bx upon partial z minus partial bz upon partial x. Right, you got some stuff in the x component, we don't care about that. Then you got partial, so for the z component you got partial y upon partial x minus partial bx upon partial y. And then for a, just have this thing, you got ax, ay, az, whatever. This is what matters, ay, az. So yeah, well, what was I gonna do? Oh yeah, this thing and then that thing. Yes, that makes sense. Sure. So you just do this times that minus this times. Wait, how is this gonna make sense though? Oh god. So that won't make sense immediately, and yeah, like this just doesn't work. Okay. Then you got this thing, a dot del of b vector. Oh, okay. What's the x component of this guy though? Right, it's just that a dot del of bx basically. Yeah, sure. So we have that stuff. Think about it. This is to x. Wait, with respect to x, you got this and you got that, right? Yeah. Az partial. Oh, that's gonna get cancelled. Sure, it's gonna get cancelled, right? Exactly. What about the y stuff though? A y partial y. Yeah, right. A y partial y of bx. No, you want bx. That's bz over there. That's not what we want. Oh, oh shit. Okay, that didn't work out. What will get cancelled? Okay, the stuff with bx is what we are looking for. This will get cancelled. Yeah, sure. This won't. This won't get cancelled, unfortunately. I wish it would, but no. Um, uh-oh. It will. It will actually get cancelled. The thing is, like, this is plus, this thing is minus, of course. So yeah, right. A, y, partially. Okay, that stuff is gonna get cancelled, sure. And then so that will get cancelled. So what you will get is like this thing, A, y, partial b, y upon partial x. Then, so this plus plus a z partial b z upon partial x. Right. But there's more parts left. I think you got two of these parts cancelled. You also want the third part, which is partial x. So a x partial with partial x of dx. Right. These two x things, these got cancelled. Cool. Then what you have is just this thing, ax partial bx upon partial x. So that's the combination of this term as well as this term. Oh yeah, that looks familiar, doesn't it? This thing, it does look familiar. It's just this thing, right? Yeah, the x component of this. Wait, not just the x component. We don't want just that. Something's not with correct. Partial b. Why is this different than what I thought it would be? It should not be vector, right? Yeah. That's only the x component, I guess. Maybe you only got like x derivatives. Wait. That's not what's supposed to be happening. No. Something. Wait. No, something must be wrong. Okay, no. Okay, the x got right. X subscript thing that got cancelled. This is still there. It has x derivatives. Okay. So that's over there. Fine. Take this partial x of this thing. Okay. Oh, well, that's kind of weird. Vector dot b vector. Shit. It's not just the x component we are looking for. What am I doing? This is not right. Oh, come on. Partial x. What was I going to do? Partial x of a vector dot b vector. Which would be what? It's just a vector dotted with partial b vector upon partial x plus b vector. Right. Okay. I messed up real big. Huh? Fine. And look at this. Look at this one and look at this. Yeah. Makes sense, right? This is exactly the same thing as this one. And then similarly, for this term and that term, you will get, like bx partial ax upon partial x, and then by partial ay upon partial x, and so on. So yeah, it will actually match up. So that's right. This does work. This is the thing, of course. Right. Yeah, that makes sense. It's perfect sense. Not just taking the partial derivative of the first term, right? Just ax bx. No, we're taking the partial derivative of ax bx plus a by plus az bz. Not just the first term. Okay. The third one. What's this thing? The divergence of f. Okay, that's different. Oh, f is not a constant, it's a scalar. Oh, okay, fine. So dotted with this guy, right? Yeah. The x component is like f a x. Exactly. So the first term, that is partial x of f a x, which is just the thing that partial x ax plus f partial ax upon partial x. So you just sum this up cyclic, and then this stuff just becomes like f the divergence of a. And what about this one though? Right, you got partial f partial x and then stuff going on. Oh right, it's just this thing. Wait, no, it's not. We get partial f and partial y. Ah, it's this thing. Okay, a vector dotted with the gradient of f. That makes sense. Is that what they're doing? Yeah, yeah, they are also doing the same stuff. A vector dotted with the gradient of f, and then f multiplied with, right, it's not of, it's multiplied with gradient of, sorry, the divergence of a. Yeah, yeah, that's right. Okay, that's awesome. Then you got a fourth one, L dot A cross B. Okay, this is going to be hard, I guess. Take something of that completely, right? Yeah. So we'll take the partial derivative of stuff. I don't know. How am I supposed to approach this? So you can write like B dot del cross A minus. Right, this is getting too much. I don't know. Is there like some easy way to approach this? I don't think so. Yeah, it doesn't look very clean. Fine. I just have to memorize this thing. There's no point in proving this. In this one as well. Just look at this. It is too big. Right. I mean, okay, this is actually something you can memorize, and then it will be useful later on. This, no way. I'm not memorizing this thing just for this little bit. Definitely not. Okay. Then you got the fifth one, which is just del cross f a. Okay, that's this thing. Ah, yeah, the same stuff as this one, right? Yeah, exactly. So, oh, it's slightly different actually. Fine. So you got what, like a cross del f. Very interesting. I mean, you can do the same stuff, right? So you can think of f and a being individual things, right? And then, yeah, like the contribution because of the change in one of them plus the contribution because of the change in other one, right? So if just the f changes and the a thing does not change, okay, then del cross a vector. Well, okay, that is change, right? Yeah, it's just a constant in that case. Um, right, it's just the usual cross product. Oh, that makes sense. Sure, it makes sense. Right, it's just like the usual dot product. Everywhere that you will encounter a partial differentiation when you will not be changing the components of A, you'll just be differentiating F basically, and that's why. Right, it's almost as if this happens. Oh yeah. Still weird though. Crossed with this guy. Fine. I mean, this is actually intuitive. It makes sense. It needs more rigor, but I'm starting to get a feel for it. Okay. In this case, like, in this case, A is a function of x, y, z, f is not. And in this case, f is a function of x, y, z, and A is not. Right? Yeah. Yes. Right. There must be some other way though, like to prove that this is the thing. Basically, what this thing is saying is that del cross with f a vector, that's just equal to del f crossed with a vector, right? That is if a vector is a constant. And how do we prove this? I don't know. I don't know about this one. Yeah, how do we actually prove this? We just have to do it, right? Yeah. I think that's a better way to do it. Okay, so the x component, what's the x component of this guy? Just got partial and partial y, partial and partial z. Over here, just got f ax on the top. but f a y and f a z, just do this and that, right? Everywhere these are just constant flows actually come out. The operation is identical with like crossing with a, just if these f were actually over here, right? Yeah, that would actually make sense. I guess so. Since every time you like do the cross product thing, you're basically just differentiating f and just doing it like a usual cross product. Might as well just put these f in here and then do the cross product, right? Which is the same as what we are doing over here. But yeah, fine. We just actually do this thing rigorously. So what's the x component? It's just a y partial f upon partial z minus a z partial f upon partial y. And over here, what's the x component? So you just got partial f upon partial z in the partial y in the y component, and partial f upon partial z in the z component. You got a y and a z, and this cross product is exactly the same as this, which is, yeah. So that just proves it that this is in fact equal to that whenever a is a constant, and yeah, basically this happens. I guess that makes sense. So, sure, it does. Yes, I think that's right. So basically, f is changing, then this, a is changing, then that. That's why just add these two things up, and you get the thing, right? I guess so, but whatever. And then you have the next, which is del crossed with a cross b, which is, I won't be doing this. I have no hope of completing this in time. Right, just move on. What you'll be using this product rule so frequently that I have put them on the inside front cover. I don't have the front cover, it's a soft copy. The proofs come straight from the product rule for ordinary derivatives. Yeah, sure. Also possible to formulate three quotient rules. Okay, fine. However, since these will be obtained quickly from the corresponding product rules, I haven't bothered to put them on the inside front cover. Yeah, whatever. It's not like we'll actually be using this in practice. Fine. Oh god. Prove product rules 1, 4, and 5. What? So 1 is easy. 4 is wait, what is this once again? Alright, like del dotted with a cross b. Guess you can do the same stuff once again, like not change a and keep changing b or something like that. But that's dotted with this thing, that's different altogether. Right. The operations, like, this is so hard. It's just so hard to do. Okay, I think I'm starting to make sense a bit over here. So this thing is like what? B dot del cross A. This thing is plus A dot B cross del, not exactly. But yeah, that's like the order of operations. If you kind of excuse that a bit, then yeah, that would make more sense given the structure in which we are multiplying. That would actually make sense. But then the order of operation does not make sense. That's why fine, you just have to do this negative sign over there. But yeah, so fourth, I can prove this. I won't. Ha. Yeah, I just won't. This I also won't because like these two are very intuitive. I get what they're doing, right? In one term they're not changing B. In one term they are not changing A, and that's why these are out of the thing, right? And also I get how they are getting this from the structure of the multiplication itself, but why do it rigorously, right? Since we'll never be using these after all. Yeah, whatever. Second derivatives, we don't care. We don't care. Okay. What do you have? This object which we write as well. Okay, the Laplacian, fine. That's called T for short is called a Laplacian of T. We shall study in detail wrong. So Okay, del square v is equal to partial. Okay, del square vx. Oh, okay, interesting. Fine. So like, okay, in this context, del square is just partial squared upon partial x squared plus partial squared upon partial x. Over there as well, right? Yeah, over there as well, just partial squared upon partial x squared, so on, right? Exactly. Here too is the same thing. This is nothing more than a conventional extension of the meaning of del squared. Okay. The curl of a gradient is always zero. Interesting. I think that's worth proving. The curl of a gradient is zero. Okay. Um, Wait. How am I going to prove this though? And just think about the x component, of course. So you got what? Just have partial t upon partial x, partial t upon partial y, partial t upon partial z, then crossed with partial upon. I mean, just think. Don't think about the x component at all. Just partial upon partial y, partial z. Cross it. You got this and this, and yeah, okay. Partial differentiation is commutative. That's why it cancels out. This is just the same thing as partial square t upon partial y partial z, and this thing is also the same thing. So it cancels out. Yeah. Okay. Right. So it hinges on the equality of cross derivatives. Yeah. Right. I think I'm being fuzzy. Test your intuition on this one. Is that always zero? So the what's this thing? The gradient of t crossed with the gradient of s. It would be, of course, if you replace dels by an ordinary vector. What? The rate of divergence for some reason seldom occurs in physical application. It doesn't. Whatever. Uh, okay, there's a lot of things going on about you. What is this? Is this always zero? I don't think so. When this represents a field, which can be any sort of thing after all, and this also represents a field, so that also can be any sort of thing. Both of these are just scalars. These two are just random vectors. So why should it necessarily be zero? It's definitely not zero all the time. Why would it be? Right? Yeah, it's not necessarily zero. No way. Okay, next what you have? Uh, the gradient of a divergence for some reason seldom occurs in physical application as well. Not being given any special name of its own, it's just the gradient of divergence. Wow. Wow. Brilliant. Notice that this thing is not the same as the Laplacian of the vector. Okay. Yeah, that makes sense. Sure. I mean, this returns a vector. This also actually returns a vector. But yeah, like partial and partial x of that stuff. Okay. Right, it's definitely not the same. Only the first term will be the same thing, partial square upon partial x square. But the other term would be like partial on partial x, partial on partial y, partial on partial x, partial on partial z. So definitely not the same thing. Okay. Right. Divergence of a curl, like the curl of a gradient, is always zero. So the divergence of a curl is zero. Cross product of that thing. Okay. Yeah, I think that. Yeah, I think that does make sense. So once again, what's the curl? It's just let's think about the x component of the curl only. What about that? Just like partial. Okay, partial one partial y, partial one partial z. Nothing of this thing. Uh, yeah, like ux, uy, uz. That's what we're doing, right? Divergence of the curl. Okay. Wait, are you saying the diverse? I was thinking of gradient. Sorry for that. Okay, the divergence of the curl. Yeah, okay, that makes sense. Sure. The x component, partial x of that guy is like okay, understood. Fine, we'll just have to calculate the whole thing and then prove it actually. So this cross with that would be what? That's just partial uz upon partial y minus partial uy upon partial z and all that stuff. Sure. And then you just do partial and partial x of the thing. So the terms are like this. In the first case, it's just based on z. So yeah, you got like partial x over there. Here you got x and y. Here you got z. The next one you got y on top. So let's see what you have. You have z over here, then minus y over here, right? Here y is the one missing from the denominator. Then what about in this case? Partial y over there, it's gonna have, well, of course x and z, something like that. First you just got x, then minus z over here, right? Then in the last one, what you have is y and minus uh, x, I think. Yeah. So right, this actually cancels out everything. And it's all in addition, of course. It's a divergence, it's not a gradient. So all of this cancels out, and guess what? You just get 0. Awesome. So that's nice. Divergence of a curl is 0, curl of a divergence is 0. We'll have to keep that in my head. You can prove this for yourself. Again, there's a fraudulent shortcut proof using the vector identity A dot B cross C is equal to A cross B dot C. What do you mean by fraudulent? Okay, so something that doesn't work with del operators, I think. Whatever. As you can check from the definition of del cross B is equal to del of del dot V minus del square D. Okay, whatever. So curl of curl gives nothing new. The first time is just it's just number 3, and the second is the Laplacian. We find the Laplacian of vector difference and creations. Whatever. We'll learn that later, right? I don't even understand what's going on with it. It's Laplacian which we seldom encounter. Okay, fine. Wait once again. What is the thing? The curl of yeah, the curl of a gradient is, wait, no, the curl of a divergence is 0. The divergence. Wait, I don't think that's going correct. Curl of a divergence, that doesn't make sense. It should be something else, right? What's the thing? Okay, the curl of a gradient is 0, right? Curl of gradient is 0, and divergence of curl is 0. Yes, that makes sense. There's nothing like curl of divergence. That would make sense because divergence needs a vector input. Okay. Fine. We could go through a similar ritual. That explains what we did. I don't know why we did all that. To work out third derivatives, and fortunate second derivatives suffice for practically all physical applications. Seriously, who even does all of this? Like, oh god. Fine. Calculate the Laplacian of the following functions. Seriously. Fine. The second derivative is to x plus with respect to y plus with respect to z. Are you serious? Okay, let's just do this thing. So second derivative, this won't survive, this won't survive, this won't survive. This will survive, you just get like 2 over there. So you got 2. For y, there's no y square terms, nothing will survive. Similarly for z, nothing survives. 2 is the Laplacian for this guy. Yep. What about this guy? Second derivative of sine, negative cosine, right? Sorry, negative sine. So it's got like negative sine x sine by sine z, and once again negative sine x sine z. Yeah, negative 3 sine x sine by sine z. That's what we are going to do. This one is more complicated but still doable. I won't do that though. Oh, that's a vector. So just, the Laplacian of this thing in the x component, Laplacian of that in the y component, in the z component. Doable, no big deal. This is going to be just 2, right? So it's like this is just 2 in the x component. Then in this case, the x, that won't survive. That also won't survive. We just do z, of course, that will survive. Just got 3x over there. CS2, it's not z. Okay, what about this one? Nope, it won't survive. It's just 0. So yeah, that's what this will have its Laplacian, right? Prove that the divergence of a curl is always 0. We just did that. Check it for functions VA. A problem 1.15. I won't do that. Prove that the curl of a gradient is always 0. We just proved that. Come on. I won't do that. Okay, integral calculus, line surface and volume integrals. This thing is just notation. Yeah, there's nothing to learn over here because we already know all this. I mean, we use this all the time. What's even there to read? Oh, yeah, this thing. A force that has this property is called conservative forces because the work done is 0 in the loop. Sure. So we know that already. Actually, that thing that the curl is 0 is for like conservative fields. This is very important. Like people might, yeah, like this may come in an exam or something like that, or You may want to use this for some unknown field, right? Okay, that's maybe just too far-fetched because we won't actually, get mathematical feeds to check out if it's considered or not in the end. Yeah, mostly it's just basically for examination purposes. It's very important. Anyway, and sadly, I learned this fact very, very late. So, I mean, I could have learned this earlier and then everything would be much more easier. But whatever. Next, calculate the line integral of this function from the point 110 to this point. Are you serious? It's just a polynomial function. Come on, don't be like that. Okay, along what kind of path though? So along the paths 1 and 2 in figure 1.21, what is this thing? The path integral of v dot dl for the loop that goes from a to b along 1 and returns. Hey, is this, like, what's the curl of this thing though? What's the curl of this thing? Is that somehow zero? Okay, I don't think that's going to be zero. No, definitely not zero because it has like y squared up in the end you get. Yeah, it's not zero. I don't think so. Definitely not zero, right? Yeah. Wait, it actually could be. Just better to actually check this thing. Let's see if the curl is really just zero. So what is the thing that you have? It's cross product, of course. Y square, then you got 2xy plus 2x. Then where's the z component? There's no z component. Okay. Since there's no z component, it doesn't actually. Yeah, fine. This is I have to actually do this thing. So, right, the first one is this and that. Oh, this does not contain z at all. So the partial and partial z stuff is going to be zero everywhere, which means, and okay, the z component is also not there. So it turns out, yeah, these two will be zero anyway. Whatever. The final z thing though, it will just be this minus that. So this guy is just 2y plus 2. Sorry. Okay, you got 2x. So wait, what? Sorry. What was the thing once again? Y plus 1, you got fine. 2y plus 2, then you got this minus of, oh god, oh god. It's not 0, it's 2k hat or 2z hat, which is different what I thought. So if it's not 0, it's this thing. Fine, whatever. So what do you want? You want to figure out this line integral for the loop that goes from a to b along 1 and returns to a along 2. Oh, this is the thing, I guess. What figure though? Figure 1.21. Yeah, this is right. So along 1 and then returns, okay, from a to b along 1 and returns 2. Okay, along 2. So this complete thing is 1. Okay, this is 2. Right. Okay, I guess we just have to actually do this thing. So along this I thing, you got this function that dotted with our dx. Yeah, just y square dx. Y square is constant. It's just constantly 1. So dx, like the change in x is just 1. So the first part is just 1. Then the next part, we are doing dy over there. This is like, okay, that's 0 over there. Got it. Yes, just 2xy plus 2x that plotted with dy. Well, x is a constant now. X is just 2. In fact, this thing's changing. So what do you get? Just like xy square plus 2xy. The change in that thing as like x is what, by the way? X is just 2. So what you get, like 2y squared plus 4y, and it goes from y is equal to 1 to 2. So this would just be 2 times of 4 minus 1, just 3, and then plus 4 times, okay, just 1. So this would just be 6 plus 4, 10. Yep. 10 is in the second part. That I selected very quickly. Yes, that seems to be the case. Yes, so it's just 10. And then in this part, right? The second part. Oh, okay. So it's like dx dy, but both of these are actually the same thing. So you can actually replace your x with y everywhere. Yeah, that makes sense. So right? What you will get is like this thing, x square dx plus 2x square plus 2x dx, and the integration of this thing x goes from 2 to 1. Wait, your dx is actually negative, so it should be negative of this guy. So that makes sense. Um, yeah. Does this make sense though? Wait, am I thinking of this correctly? It's got to be negative, right? Because you're this is actually positive, that's actually negative, so it's got to be negative. So this is already negative. It's supposed to be like this. Yeah, that's the thing. No need for an extra negative. That would actually not make sense. Dx is already negative. That is in it. You don't have to add an extra negative. Fine. What is this thing going to be? It's just the integration of 3x squared plus 2x, right? Which is this called x cube plus x squared, and it's going from 1 to 2, or 2 to 1, sorry. So that's just 8 minus 1 is 7, okay, plus 4 minus 1 is 3, I think. Negative of that, 8 of 10 cancels, you get 1 as the thing. So 1 is what it's gonna be. Okay, cool. uh yeah, that should probably do it. Okay, is there some better way of, oh, there's also that other thing that you can do, so that you just do z hat, right? Yeah, that's our curl is just 2z hat. So if I do the, what do you call it, like the Green's theorem, right? That's what they call it. So I already did that in that video, so you should actually watch that to get what I'm doing right now. Right, so 2z hat is our curl, that with our area vector. Okay, it should be the integral, but now it's just the same everywhere. So just dotted with the area vector, which is, what's this length? It's just 1. This thing is 1. It's just half is the area, so that half is just 1. Right. So what do you get? Just 1 is equal to this line. Oh yeah, 1 is equal to this line integral. That's exactly what we got as well. Easy. Very easy, in fact. So whenever you, yeah, whenever you get the curl to be a constant, just multiply by the area of our loop. There you go. You got the line integral. Easy as that. Okay, next. Oh, this is oh god, this is an example. I thought I had to do this thing. Are you serious? I did all that for nothing? It's not a problem. Ah, seriously. Fine. Next thing is surface integrals. We already know this. So they are using ds. No, they are using d small a. Weird. I use d capital A vector. Fine. Okay, outward is positive. Yeah, traditionally that's what they do. But for open surfaces, it's arbitrary. If V describes the flow of a fluid, mass per unit area per unit time, then this thing represents the total mass per unit time. Right, so like the flux as in the volume flow rate or something like that, right? That's what they're talking about. Or the current flow rate. That would also make sense. Yes, I get that. We shall soon be in the position to characterize the special case. What the special case? Ordinary value of surface integral depends on the particular surface chosen, but there is a special case of a vector function for which it is independent of the surface, but it has been boundary line. Okay, whatever. Calculate the surface integral of this thing over the what 5 sides, excluding the bottom of a cubical box. I don't want to do this thing. There's just a lot of work. Oh, it's an example. Nice, nice. Look, I told you it's a lot of work. Look at this. Look at the amount of cases they actually have to make to just do this thing. 5 cases for 5 sides. Yeah. Okay, except for flux is this thing. Whatever. Volume integrals. Once again, we know this notation. This gamma thing is for volume. Square function reduce some volume element. Oh, okay. So they're using d tau. I use dv usually, but fine. Okay, like capital V is reserved for potential, so I think they fine. That's why they're using tau over there. Cartesian coordinates beta is equal to x. Example d is the yeah, whatever. Calculate the volume integral of this thing over a prism in figure 1. But once again, an example. I'm not gonna do that. Oh, you got a problem now. Calculate the line integral of the function from the origin to the point 1, 1, 1 by different routes. line integral of this function from the origin to 111 by three different routes. That straight line, what is it? Whatever. Hey, I guess we should actually figure out what's the curl of this thing, right? Because who knows, it might just be zero. There's no z component at all, so interesting. What do you have? Just got x squared, then 2x. Wait, what? 2yz? Oh, it doesn't look like it's going to be zero. Whatever, let's figure it out. What's the x component going to be though? It's just this is 2y minus 2y. Nice. And for this, let's just 0 minus that was a 0. Awesome. If I just got this thing, which is 0 once again, that was a 0. Yeah, that is 0. So the curl is 0, and right, just gotta do it for one path, and there you go. So you want to go from where to where? To the origin to a point 111 by three different routes. Yeah, first we just move along the x, then along y, then along z, and so on. We get the thing, right? Okay, I'll just go with the first route first. So first just along x, right? Your y and z values are just 0, right? Throughout. So these two components are not there anyway. It's not that actually that matters because those will be 0 anyway, right? Dot dy dot dz stuff, well, dy is 0, dz is 0. Okay, this is just x squared dx. Integration of that is x upon 3 is going from 0 to something like x upon 3 thing. It's just 1. So 1 upon 3 is the first. Yeah, the first part is just 1 upon 3. Then the next part will be, so you're going from 1 comma 0 to so right, just doing with y. What's y z? Well, z is 0. Nice. The whole integral is 0 in that case. Then you got this last stuff where you're moving along z. Okay, so you got y squared z hat, right? What's y squared as you move along this thing? It's just 1. So dz, just dz. Integration of that, just z. Changing that, just 1. So that's the thing. It's just 4/3. 4/3 is this line integral in all cases. You know, you don't believe that? I'm going to do it for the second case as well. Okay. So you got z over there is y squared. Y squared is 0. That's gone. Fine. Then right, you're moving along y over there to yz dy, and your z is 1, your y is changing, so just 2y dy basically y squared to change in that. Right, just 1 of course, it's 1 of course, plus, so you got x squared. Cool, doesn't matter what y and z are, just moving from 0 to 1 in the x direction, so it's 1 upon 3 of course. So it's also 4 upon 3. No surprise because that's the way it is. The curl is 0. Okay, that's awesome. Then you got a direct straight line. You wanna figure out what? Oh, it's just going from there to there. That's also gonna be 4 upon 3, right? Yeah. Of course, 4 upon 3. You can do it like this thing. You just do, let's just say x is equal to y is equal to z is equal to r, right? That's how we will parameterize the thing. I should not say r. I should actually say t. Yeah, t. That's a nice parameter. So this will be the integration from t is equal to 0 to 1. Our dr vector is just dt times 1 1 1, right? Yeah, and our v vector is just t square comma 2t square comma t square. So that ought to be this guy. Fine. It's like t square, and then you got 1 2 1. This dotted with dt 1 1 1, which is just 4 t squared dt. So you got 4/3 t cube 0 to 1 4/3. That's the thing. Awesome. What is the line integral around a closed loop that goes out along A and back along path B? 0. Come on, really? That's pretty obvious that when you go in reverse direction along B, every single infinitesimal thing that you are going to add, well, it's down to negative of that because your dr vector is negative of what it was when you were originally going along the path, right? So this will just be negative 4/3 for the, yeah, when you're going back along path B, 4/3. Sorry, negative 4/3. So this would be 0. Yeah, that's line integral. Okay. Problem 1.29. Give the surface integral of the function in exercise 1.7 and the bottom of the box, over the bottom of the box. Okay. For consistency, let upward with a positive direction. Does the surface integral depend only on the boundary line of this function? What is the total flux for the closed surface of the box, including the bottom? Note for closed surface, the positive direction. Wait, what's 1.7? Says 1.7. Where's that? This is 1.8. 1.7 is this. Wait. Okay, surface integral of this thing over 5. Oh, I'm not gonna do that. I'm not gonna do that. Definitely not. It's a lot of work. Wait, just the bottom, right? Are you are you sure? Wait. Okay, over the bottom of the box. Ah, fine. So you don't have to do 5 cases, you just have to do one. Nice. Okay, so how's the box, by the way? Wait, this is 1.7. That's what we want to do, right? Yeah. So the angle of this thing on 5 sides is to the bottom of the cubical box in figure 1.23. Where's that? This is 1.23. This is XYZ coordinate. This is our origin, I guess. Bottom of the box is this thing, of course. Alright, so it's x going from 0 to 2, y going from 0 to 2. Just want to integrate this thing. Of course, the double integral. Yeah, you think. Just the double integral from 0 to 2, 0 to 2, dx dy. What's our function? What's our function? Oh, and also like this dotted with our dA vector. So that's just like this, and then you got z hat. So only the z component is what matters, which is y times z from s3. Z is 0 for our bottom part, so it's negative 3y. Yeah. Trying to get this guy. But 0 to 2 of something that's not dependent on x at all, just like 2 times of this guy, which is, yeah, that's gonna be the thing. So just negative 6y dy is integrated from 0 to 2. Sorry. Sorry for that. So it's negative 12. That's our surface integral. Easy. Okay, what were you saying, by the way? Oh, that's what I wanted to do. Right, technically the surface integral of the function in 1.7 over the bottom of the box. I did it for fine. Yeah. Does the surface integral depend only on the boundary line for this function? What is the total flux over the closed surface of the box, including the bottom? Note, for the cubical surface, the positive direction is outward and hence down for the bottom surface. Only the boundary of the box, huh? What kind of thing would depend on that only? If this was a curl of something, right? Yeah, wait a second, is that a curl of something? Because then you can apply Green's theorem or something like that. Where's 1.7? The function vector format is like 2xz, x plus 2, the curl of something. What kind of property does a curl have? That its divergence is 0. Right. What's its divergence? It's just 2z, then it's like it's y to 0 over there. Then you got with respect to z, which we 2yz. That's not what we want. No, that's definitely not what we want. Okay. Hey, but the curl is 0, right? No, okay, sorry, the divergence of this thing is, it's not 0. No, it's not 0. This is kind of weird. Am I missing something? If this is actually the curl of something, its divergence has to be 0. Sure, I did the thing. It turns out it's not always 0. So what do we say? It's not a curl of something. So it's not like we can't apply Green's theorem. Sure. So what else can we apply? Why would it only depend on the boundary and not the surface? Okay, I get it. Like if you have the same boundary and then you have some other kind of surface, Green's theorem basically says that it doesn't matter what kind of surface you have, as long as it's the same boundary, the surface integral for a curve kind of function, that's going to be the same. So if this was actually a curve of something, It would have made sense. But if it was a curl of something, then its divergence must be zero, which it is not, right? It should be zero at every single place, which it's not, definitely. Yeah, that's what it is. It's not zero. Right, go on. Okay. I don't get it. Why did they ask me this question if this was not? I don't get it. The bottom. But whatever, just move on. Fine. For the 1.3, calculate the volume integral of the function t equal to z square or over a tetrahedron with corners at this, whatever. Volume integral of this function t equal to z square over a tetrahedron. Are you? Wait, what? Tetrahedron. Um, so that's one vertex, or just got one. So draw it out. Best way is just to draw it out first of all. So this thing is your x-axis. This is your y-axis. This is your z-axis. The first point is just the origin. Okay, then you got 1 comma 0, x equal to 1. Cool. Then y equal to 1. This thing, and then like you got z equal to 1 over there. Got it. So you want to find the volume integral of this thing, t equal to z square. You can of course integrate along z, but what's the area of this thin slice, right? Because you want dv. Well, dv could take different kinds of shapes. In our case, we could take the shape of a slice of this tetrahedron, like this, you know, right? Yeah. So first of all, what's the base area of this thing? Is just half. Uh, yeah, and that is when z is equal to 0. At this point, z equal to 1, it will just be, yeah, that's 0 over there. So 1 minus z, that's the fraction of the area that actually you have, because it's linearly decreasing. That's pretty obvious, isn't it? Oh, it's not just that. In fact, it's like the square of this thing. Isn't that right? Because x changes linearly. It changes by, yeah, the area changes by a square, of course. So 1 minus z squared. Yes, that makes sense. Whenever z equal to 0, this would just be 1, and then, right. Got to be the thing. That's got to be the thing. So 1 minus z squared, and that times the base area, just half. So, yeah, that's our dA thing. That times of dH, it's just dz, of course. Okay, that's our dV element, and this times of z squared. That's our f dV. So you want to integrate this thing from z is equal to, you know, 0 to 1. That's it. That's it. Yeah. Okay, let's figure it out. Oh, it's gonna be hard. I'm trying to think it's like symmetric or something. It sure is symmetric. Not exactly the way that I think it would be though. Just do it. There's no point in, just do it. So you got z squared times z squared minus 2z plus 1 dz. It's from 0 to 1, of course. You got a half. Z power 4 is z power 5 upon 5, just 1 upon 5 in that case, minus 2 z power 3. So just z power 4 upon 4. It's like 1 upon 2, and then you got 1. Right. Z power 4, just 1. Sure. Am I doing this correctly? I think I am. Okay, then you got plus z squared like this 2 upon 3, just 1 upon 3 over there. Cool. So yeah, that should be our volume integral, I guess. Which is like what? 1 upon 2, then you got 1 upon 5 minus 1, whatever. Power 2 minus 5 is just negative 3 upon 10 plus 1 upon 3. This is the half of, you got negative 9% is 1 upon 30, but 1 upon 60 is the value. So that's this volume integral. Cool. Next thing, you got fundamental theorem of calculus. Yeah, we already know that. You got integral calculus. What is this thing? Right. I mean, even kids know this stuff. Okay. Then you got fundamental theorem of gradients. What's this thing? This makes sense because this thing is like the directional derivative, right? Yeah, like not exactly like that, but then Is there like a directional differential? That would have made sense. Uh, yeah, dotted with this guy. Thing is like gradient of t dotted with L hat. That's a directional derivative that dotted with just dl, not dl vector, just dl. Right, that would be the directional derivative times dl thing. Whatever. But yeah, this thing is definitely a dt. So just the integration of dt, that is of course the change in t, which is t of whatever b represents, t at that position minus t at the position a. Okay, right. So a and b are points. Fine. Oh, that's why in bold these are actually vectors, huh? Okay. So now we are inputting vectors into functions. Well, I mean that is a way to think about it. Instead of putting three inputs, we are just putting a vector. Makes sense. Okay. Right, we get that. Since fundamental theorem of gradients, like the ordinary differential, ordinary fundamental theorem, it says that the integral for derivative is given by the value of the function box. Yeah, yeah, whatever. Geometrical integration. We don't need that. 1 point. Okay, it's an example. We won't be doing that. 1.31. Check the fundamental theorem of gradients using t equal to this function. The points a is given by this thing, b is given by this thing, and the three paths in figure 1.28. Really? Are you serious? Do I actually have to do this? I mean, I have to take the gradient and then I actually have to. Are you serious? I just did it, right? And now you want me to do this once again? I mean, I just hit the gradient to get the different. Yeah, God. You just want the derivative and now you want me to figure out the integral. It's pointless. It's like that kind of activity that they would, tell you to do in like ninth grade or something, where you have to verify Pythagoras theorem by geometry. No, not geometry, like by areas or something like that. You know it's going to be true, and yet you have to do that. I'm not going to do this. No, you already know it's true. Believe in maths. Another theorem of divergence. Oh yeah, this thing. It's called divergence theorem. In fact, right. In honor, I suppose it's okay of its Green Poisson theorem has at least three special names: Gauss's theorem, Green's theorem. This is also Green's theorem. Oh, but isn't the curl theorem the Green's theorem? I don't know, or simply the divergence. Yeah, the divergence theorem. That's what we call it, right? Like the other fundamental theorem, it says the integral of a derivative is equal to the value of this function at the boundary. Yeah, whatever. So I have a proof of this thing in that video. You should watch that. Actually, that's not actually a proof. It's more like from the definition itself, you can just get this directly. So no need for proving this as such. Fine. Okay, so he's giving some kind of physical interpretation. I don't need that. The math is good enough. Sure, you can think of field lines as things flowing out or something like that, but why? Why would you want to do that? Sure, you can think of the surface integral as some kind of like increase in volume per unit time, something like that. Why would you do that, right? When you can just do maths. Okay, this is just an example, I think. Problem 1.32, test the divergence theorem for the function, this function. Take your volume as the cube in 1.30. Okay, with the sides of 2. Fine, so first we'll just have to do the volume integral of our, what do we call it, the divergence for sure. So the divergence of v is what? It's just y plus 2z plus 3x, right? You wanna integrate this thing, the triple integral, of course, right? Yeah, so first we'll integrate with respect to x. You just get like what? Y plus 2z times x plus 3x square upon 2. And now this thing goes from x is equal to, I guess, yeah, it's just the function is dependent on x, y, z, so it should be just the integral like this thing. Yes, surely that's the thing. So x is going from what to what? Just 0 to 2, I think, right? Which would be what, like 2 times of y plus 2z plus 2 times of 3. So in the end, we get like 2 times, or just do it this way: 2y plus 4z plus 6, right? and then integrate this through y. So just get like y squared plus 4z plus 6 times y, and goes from 0 to 2 once again, right? Yeah, so like giving z constant, something like that. Yeah, yes, that makes sense. So what is this thing going to be now? It's just 4 plus 2 over there, right? Yes, yeah. So we got 8z plus 12, which is just 8z plus 16. Now we're going to integrate this guy with z, of course, which is just got 4z squared over there. It's like 4 times 4, so 16. 16 plus 16 times 2, because z 0 to 2, right? So it's 32, which would be 48 or something. Yeah, so we got 48. And if this is correct, then okay, let's try it out. Let's try the uh, the surface integral of this function over these 6 surfaces. Okay, let's go for, oh, this is going to be hard. 6 surfaces, huh? The first case, okay, let's just read this thing: x, y, z, serial number 1, 2, 3, 4, 5, 6, right? What's the flux in each of these cases? Okay, what's the value of x, y, z? I mean the boundaries, of course. Wait, oh god, we'll need boundaries, not just values. Uh, Shit. This was unexpected. Okay, fine. Just do it. Just do it the way it's supposed to be. So first of all, just do the x direction stuff. So the flux in the x direction. Uh, about this surface, well, our v vector is just okay. X is 0. This thing is gone. Our area vector is in the x hat direct. Yeah. So that just means the first component is all we care about is x, y, dx, and the integral of that guy. So in this case, our y is 0. Wait, that's y? Like, you know what? No, just ignore that. Just like this thing is x, this thing is y. This, yeah, whatever. I'm gonna make a new system for this thing. This thing is x, this thing is y, this thing is z. Fine. Okay. Right, the surface integral. It should be going out. Okay, cool. So this is actually a very bad drawing. Like it. Fine. So first the x surfaces, perpendicular x surfaces. This has 0 because like, yeah, x is equal to 0 in this whole thing. So the first component is 0 anyway. What about this one? Oh, and it has the area vector pointing in this direction. This has in that direction. Good. Right. This has the value. It's like x is what? X is just, God, what was x once again? Ah, what was x once again? X was just 2, right? Yes, like you got 2y. 2, yeah, I just want to do this thing. 2y, the double integral of this thing, dy dz, changing y and z, right? So our y is going from 0 to 2, z is going from 0 to 2. Okay, cool. So you want y square over this 4z, that guy. Yeah, 4 dz, sorry. Uh, yes, 4 dz, so just 4 times of just 8. So that's 8 flux x plus y is, so this and that. Okay, cool. This is just 2yz over there. Why is this so weird though? Hey, I think we can just say symmetry and call it a day, and like it's just 2 times of this guy, just 16, right? Of course, the value will be higher over here, right? I mean, okay, in this phase and in this phase and in this phase, in these 3 phases, one of these must be 0 anyway, right? So yeah, I get that. So be 0 anyway. And when it like it's this thing, um, right, it's not 0, it's like y equal to 2 or something. And then it's the same thing once again. It's positive. I get that. I'm starting to get that actually. Cool. So what do you get in that case? It is just 2 times of this guy, just like 16. And in this case, 3 times of that guy. Just yeah, like 1 plus 2 plus 3 is 6 times 8, 48. 48 is what we'll get. Here as well we got 48. So that proves it. It is the same thing. In this case, the volume integral was easier for some reason. I don't know. Okay, nice. Next, fundamental theorem of curls. I use it's called the fundamental theorem of curls. I should have searched by that everywhere I was learning for this. Okay, the fundamental theorem of curls, which goes by the special name of Stokes theorem. It's not Green's theorem, it's Stokes theorem. God, till now I've been thinking it's like it's Green's theorem. Is it not? Wikipedia says it's Green theorem, sir. It's Green theorem, right? I don't know. Doesn't look correct. Anyway, next. Uh, we already know this, right? I mean, I proved that. Okay, got integral calculus. That thing is going on anyway. Okay, let's just, what is this thing? Okay, the for any closed surface, it's the boundary line like the south of the dimension. Right. Okay. So for a closed surface, let's just say a sphere, for example, you can do what you can do is like you can split it into two halves. Think of the upper half first. You got this hemisphere. Um, right. Our area elements, we just say it's like convention is just pointing outside, right? So yeah, in this case, it's just pointing outside. The total area element would be pointing in this direction or whatever. So by right hand rule, what should be happening is that we should be going in this direction, but then over here it's in the opposite direction. So like we should be going in this direction, right? So that since these are like conflicting and yeah coincident as well, so what would happen is that the line integrals would actually cancel out. So right, I mean the line integrals of the function itself. So the surface integrals of our curve, that like okay the sum of those two basically, that also cancels, so you just get zero. That's why this thing is true. Yeah, that's very correct. This is zero for any closed surface. Is the boundary since the boundary line like the mouth of a balloon shrinks down to a point and hence the right side of equation okay vanishes whatever. Polaries are analogous to those for gradient theorem, which shall develop the parallel further in due future. Okay, whatever. Then you got another example. How large is this chapter? Okay, problems. Sorry. Test strokes theorems. I'm not gonna do that. Wait, didn't I just do that though? No, no, I didn't actually do. No, I did Green's theorem, right? Yeah. Okay, I did the volume integral somewhere, which means I did. Yeah. Okay, divergence theorem. Fine. Now we're gonna prove this Stokes theorem. I mean, we're gonna find evidence for Stokes theorem by seeing if this works for that. Ah, using the triangular shaded region of figure 1.34. So this thing, okay. So y and z, got it. Uh, fine, I guess. Right. What's our dv element going to be? Will indicate along z actually. Right. So if this is along z, then it's like this thing. 2 minus z upon 2. That's the fraction of this, right? Well, that times of this completely and just 2 over there. Okay, that's yeah, that's what this length will be. Well, this times of our dz. Right. This is our the length along y or something. This is weird. Okay, this times of dz. So this cancels. Basically, what you get like 2 minus z dz. That's our dA element. Yeah. Right. Then you want dA times. Hey, wait a second. Our area element is supposed to be pointing in the x direction. In the x direction, we've got xy only. So the z thing does not matter. Oh shit. Okay, you want something that has the same z value. Right. This strip that we talk. So what I'm doing is basically this thing. I'm thinking of our dV volume is something like this. I know that's not how we're supposed to be doing it because it might be possible that over here the thing is different than what is thing over here, right? Oh shit. This thing is the function itself. We just want the oh god, we want the curl of this thing, right? Yeah, we want the curl first. Ah, are you serious? Fine. and this area is in the x direction only, so we want only the x component of this guy. First, you're going to do partial y of the z component, which is just, well, 0. Awesome. Minus the partial z of the y component, which is 2y. Okay, that's 2y. Fine. So our curl is just minus 2y. Right. And you want to integrate this thing over this area. Okay. How am I going to do that though? We have to get along y. So, right, it's like y to be something. We want z to be something. So that, wait, no. You want the y to be, okay, right. Our y should be fixed so that the curl is the same thing for that whole strip, and then you can use that as the area limit. Right, that makes sense. Okay, so this strip is what we're talking about. So what's this length going to be? This length, if this thing is y, this is 2 minus y, and that's like 2 minus y upon 2, so this fraction, but you get a thing, all the same, is just 2 minus y is what this length will be, because this thing is y as well. Yeah, whatever. Fine, so you got 2 minus y, it's this length, then this times of this length, which is dy in this case. Okay, that's our dA element. This times the, where's the area element supposed to be going to? It's negative 2y, huh? This thing is in, oh, okay, the path is in this direction, fine. So, right. So we gotta do the, yeah, we have to multiply this with x hat, right? Not negative x hat, fine. So when we multiply by negative, when we multiply by just x hat, you get this thing for our, divergence. Shit. The curl, sorry, right? The curl dotted with x hat is just this thing. So multiply by that, right? Yeah. In the sense of negative 2y. That's our integrand. Integrate this thing from y is equal to 0 to 2. Yeah, that is the thing. That's our surface integral. Cool. Which is what? Just minus 4y plus 2y squared dy. Addition of this guy, just negative 2y squared plus 2 third y cubed. Going from 0 to 2, of course. It's just negative. Got 8. Yeah, 8. Plus, this thing is what? 8 plus 16 upon 3 or something. 24. It's negative 8. 8 upon 3. Got it. Yeah, supposed to think. Right, so this is just negative 8 upon 3. That's what this surface integral is supposed to be. Yes. Right, and now let's figure out what this line integral will be. So you're going from here to here, your z is fixed, your x is fixed, is both are just 0. Your y limit, right, just this dot with dy. Well, this is actually 0 anyway. So nothing changed over here. Then you're going from there to there. Your x is fixed is, oh, and this thing, it's really different than what I thought. We'll have to parameterize this thing, right? Okay. So this line is just x plus y is equal to 2. So what, sorry, y plus z equal to 2, sorry. Right. So what we'll say is just that y is 2 minus t and z is t, right? And then, right, got x over there as well. So x is 0. That's our r vector. Now our dr vector as we move in this direction, right? So when t equal to 0, what exactly happens? It's just y equal to 2, which is at this point. So as t increases, you go to this direction. So like this times, yeah, okay, differential of this guy, which is just, negative dt comma dt. Right. That's our dr in this direction, right? Exactly. Dot this thing with this vector, right? So you should have 0 as the x component, of course. Then you got something in y, something in z. Oh god, dt. Negative of this guy, just need 2yz, then plus, oh, x is 0. Awesome. That just doesn't matter in the end, right? You know what, like, okay, these two things don't matter at all. They just y hat. That's the only component that actually matters. Awesome. Anyway, this is the thing. Yeah, like integration of this thing from t equal to 0 to what? To 2, right? Yeah, 2 of, god, this thing is minus 2. What's our y? Y thing is just 2 minus t. and z is just t, and dt is there, of course. Yeah, that's what we think. That's what we think. So this is what just negative. Right, dt, which is negative 2t squared. That looks familiar, doesn't it? 2t upon 3 going from 0 to 2. So just negative 8 plus, yeah, it does look familiar. It's just negative 8 upon 3. So the same value. And then I guess in this is just going to be 0 because these two will be 0 anyway and it's moving along the z hat direction. So okay, it's 0. Yeah, it's 0. So that explains it. It's the same thing. Negative 8 third, negative 8 third. Cool. Okay, next. Just another Just another check this kind of problem. I'm going to do that. Additional parts. I know this technique. Next, evaluate this integral 0 to infinity of x e power negative x dx. Hey, that's actually a nice function. E power negative x, it's doable, right? And then x, yeah, we can do that. No big deal. So what do you do? Just integrate this guy. First of all, the indefinite integral of this thing. So just integrate this thing, e power negative x. Um, right, it's e power negative x integral of this guy. Put x in front. Then negative is like positive integration of differentiate x, just get 1 over there, and then you got e power negative x dx, which is, yeah, just negative e power negative x, like negative e power negative x, and then you got x plus 1, easy. So that's what the indefinite integral is. Now I just want this to be going from 0 to infinity. So at infinity, this thing just becomes like, okay, x plus 1 upon e power x, which one wins? E power x wins, right? It's much bigger than any kind of polynomial function. So yeah, that will just become 0, and then you use this negative to actually change this. It's like from 0 to, it's from infinity to 0. So at infinity it will be 0, and at 0 it will be e power negative 0, just 1, and then you got something just 1. So this is just 1. Yep, next question. 3x. Oh, this is oh god, it's an example. I thought it was something else. Okay, next. Well, this is new. I never thought about this. Integration of parts in multivariable calculus, huh? Okay, this is something I've never seen. And there's more proofs. Then you got curvilinear coordinates. Hey, this thing, I think I have done a bit of stuff on this, like, gradient and divergence in spherical coordinates. Right. I think I've done that. Uh, I'll probably have to write that in my note once again. Anyway, I guess we should stop here. So I'll see you guys next video. Bye.